Hey guys, welcome to Rocky Biochem series. In this tutorial, I will take you through the refrigeration system. Kindly support my channel by subscribing for me. Thank you very much. From the second law of thermodynamics, heat flows spontaneously in a direction of decreasing temperature. In other words, heat flows spontaneously from a region of higher temperature to a region of lower temperature. However, in refrigeration, we try to violate this rule by trying to transfer heat from a region of lower temperature to a region of higher temperature. We can therefore define refrigeration as a process involving the removal of heat from a body whose temperature is lower than that of the surrounding. And this can only be made possible by using some special working fluids called refrigerants. Refrigerants are therefore heat-carrying medium, which during refrigeration cycle absorb heat from a low temperature region and then discard it to a higher temperature surrounding. So you realize that the inside of the fridge is normally cooler as compared to that of the surrounding temperature. So we are able to transfer heat from that region to the external environment, and this is only made possible by using refrigerants. For a substance to be used as a refrigerant, it should be able to possess certain properties, and some of them include low boiling point. It should have low boiling point in order to enable it boil, even when small amount of heat is supplied to it. And also, it should have higher latent heat of vaporization, so that with a supply of small amount of heat, the fluid will vaporize from the liquid state to the vapor state. And it should also not be toxic, so that when it is consumed, it will not be harmful or lethal to the health of mankind. And also, a refrigerant should have higher critical temperature. A critical temperature is the temperature beyond which a vapor will fail to liquefy. So when the critical temperature is very high, it implies that no matter how the refrigerant will be superheated, it will never reach the critical temperature so that it will fail to, vaporize, or it will fail to condense back to the liquid state. We always want the refrigerant to condense from the vapor state to the liquid state. That is why we expect it to have a very higher critical temperature, so that no matter the amount of heat supplied to it, the critical temperature will not be reached. And also, it should be able to have higher thermal conductivity, so that it will be able to convey heat effectively. And again, it should have low operating pressure. That is, it should be able to operate at lower pressure, as that will enable us conserve, cost and then energy as well. It will enable us to conserve maintenance cost and at the same time conserve energy. There are different types of refrigerants available. We have the halocarbons, and they include the R1, R2, R22, R40, R133, etc. And we collectively call this group of refrigerants freons. We call them freons. That is why sometimes you will come across freon 11, freon 12, freon 22, and then etc. We also have the hydrocarbon based refrigerants, and they include ethane, propane, isobutane, and then etc. You can also use some inorganic compounds as refrigerants, and they include carbon dioxide, ammonia, sulfur dioxide, and then many other more. We also have a certain group called the azeotrope. Azeotropes are normally combination of hydrocarbons and sometimes the halocarbons as well. Now, let's move on to understand the general principle of refrigeration. Before we will proceed to talk about the calculation aspect, it is very relevant for us to understand the general principle so that we will appreciate whatever we will be doing. The first thing that I want you to put in mind is that anytime you have a liquid and then it vaporizes, or when you have a liquid and then it evaporates, it absorbs heat. So let's say I have water at 100 degrees Celsius and the water begins to reach boiling point and then evaporates. As it is evaporating, it does what? It absorbs temperature, or it absorbs heat. it absorbs heat. But when you have a vapor and then it is condensing to liquid state, it does what? It rejects heat to the environment. So condensation brings about rejection of heat, whilst evaporation brings about what? Absorption of heat. This is the first principle that I want you to put in mind before I talk about the general principle of refrigeration. Let's consider this refrigerator. When you consider your refrigerators at home or at even workplaces, it normally have two compartments. We have the freezer and then the normal fridge, region. So you realize that at the freezer portion, there are some coils at that particular, there are some coils normally, beneath the freezer region there. So these coils are called the evaporators. These coils are called the evaporators. So the refrigerant flows through these evaporator coils, and as it flows through the evaporator coils, it exchanges heat exchange between the food that is placed in the fridge and then the refrigerant occurs. So when you put the food in the fridge, or like when you put the food in the freezer region here, since the food is hotter than the refrigerant that is flowing through the evaporator coils, heat will then move from the food and then that heat will be absorbed by the refrigerants that are flowing in the evaporator coils. And as I said earlier, anytime a fluid absorbs heat, anytime a fluid evaporates, we say that it has absorbed heat. So when this heat is transferred from the food to the refrigerants that are flowing in the coils, then the refrigerants will be converted from liquid state to vapor state. In other words, they will turn from liquid state into saturated vapor. So the refrigerants that are flowing in the coil, after they absorb the heat from the food, they will turn into saturated vapor. So they will flow all the way, like the saturated vapor will be compressed at by the compressor. You see, there is this black portion here that is normally located at the back of the fridge. It is called the compressor. So this compressor will compress the superheated heat, we call the superheated refrigerant. And then by compressing it, it will bring about increasing in pressure and then increasing temperature. We know that pressure is directly proportional to temperature. P is directly proportional to temperature. From even this law, PV is equal to nRT. We know that P is directly proportional to temperature. So anytime pressure increases, temperature also increases. So when the compressor compresses the saturated refrigerant, it causes an increase in pressure and then increase in temperature at the same time. So this will bring about the saturated vapor now becoming a superheated liquid. It's a superheated vapor, sorry. It enables it to be what? Superheated. So when it becomes superheated, then it will flow into the condenser. The condenser is normally that metallic coils located at the back of the fridge. So as the saturated superheated refrigerants enter the condenser, it will begin to flow through it, and then as it flows through it, the condenser makes it exchange heat with the surrounding temperature. So it will condense. The condenser just condenses the superheated vapor back to liquid state. And as the condensation occurs, it will reject heat. As I said, anytime condensation occurs, heat is rejected. So the condensation will occur in the condenser region, and then heat will be rejected into the surrounding temperature. And after that, the the refrigerant will now be in a form of liquid. It will be in a form of saturated liquid, and then it will flow into the expansion valve, where expansion of the fluid will occur, and then the temperature will fall drastically as well. And after that, it will enter the evaporator coils again, and the cycle will continue. This is basically how a fridge or a refrigerator works. This is basically how a refrigerator works. Now, let me continue with the refrigeration cycle, although I have already given a general overview of how a refrigerator works. So let's continue with the refrigeration cycle. The whole cycle starts from the evaporator region. You see, the evaporator region is normally, as I said, the region located inside the freezer portion of the fridge. So the heat will flow spontaneously from the food into the refrigerants that are flowing in the evaporator coils. And as the heat flows from the food to the refrigerants in the evaporator coils, the vaporize and then becomes saturated vapor. So the saturated vapor, that is the refrigerant which is existing as saturated vapor, will leave the evaporator and then enter the compressor region. So when it gets into the compressor region, the compressor will compress the saturated vapor isentropically, that is constant entropy, and then it will become a superheated vapor. You see, when you compress a substance, the pressure on it increases, and pressure is directly proportional to temperature. That is why after the compression, the temperature of the saturated vapor also increases to become a superheated vapor. And after it becomes superheated, then some amount of the superheat will be removed, and then it will enter the condenser region. As the name implies, condenser, so it will condense the vapor back to liquid stage. And as condensation occurs, heat will be rejected to the surrounding temperature. And after that, the refrigerant will then leave the condenser as a saturated liquid. It is only the condenser region that the refrigerant will start living as a saturated liquid. So after living as a saturated liquid, it will then enter the expansion valve where expansion will occur, and then the temperature of the refrigerant will then allow to drop to lower temperature. And after that, it will enter the evaporator coils again, and then the cycle will continue. Now, let me move on to talk about pressure enthalpy charts. The whole of the refrigeration cycle can be represented by using the pressure enthalpy chart. So as you can see, we started by we started at maybe the point one here. Let's say where the first arrow here, as you can see from here, this is the evaporator region. So the whole of point one here represent the evaporator region. So at point one, we absorb the heat from the food, and after that, it got into the compressor region where compression occurs. So the compressor compressed the saturated vapor from point one all the way to point two, and after that it became a superheated liquid. So at point two, the refrigerant is existing as a superheated vapor. So after it exists at that, some amount of superheat will be removed, and then it will reach point two. That is 2 prime here, the point 2 prime here. And from the point 2 prime here, that is the condenser region. So heat will be removed from the saturated vapor through the condensation process, and after that it will exist as a saturated liquid where it will get back to the evaporator, where it will get back to the expansion valve, and then cooling will occur, and then it will get back to the evaporator region to continue the whole cycle. There are some deductions that I want you to take note of. As you can see from here, as you can see from the graph here, the point 4 and then the point 1 are at the same pressure. The point 4 and then the point 1 are at the same pressure. So the fluid that moves from the expansion valve to the evaporator moves at a constant pressure. Pressure does not change. But as you can see, the compression for the compression process, that is from point 1 to point 2, we can see that the pressure has increased from 1 to 2. The pressure has increased, though entropy was remaining constant, but pressure has increased. And as you can see also, we can see from here that the enthalpy 3, that is H3, is equal to H4 because they are on the same level. They are on the same level. That is why H3 is equal to H4. But H1 will be different from that of H2 prime and that of H2. So this is basically how a pressure enthalpy chart looks like. We will be using this for most of the calculations that we will be doing. So I want to take you through okay, I think I made mention of this, that S1, that is the entropy 1, should be equal to entropy 2 because for the compression process, that is the region where I have indicated by red dots, we can see that that is the compression process. And for the compression process, it was done at a constant entropy. It was done isentropically. That is why we expect the first entropy, that is the entropy at point 1, to be equal to the entropy at point 2. But we don't know the temperature 2 here. For the temperature 2, that is the T2 here, the temperature of the superheated vapor. You see, after the compression, the refrigerant will exist as a superheated vapor. indicated by zero point 0.2. So we don't know the temperature at the zero point 0.2 here. That temperature is obviously different from the temperature at the condenser region and that of the evaporator region. That particular temperature is different. And if you want to know it, we use this particular formula. That is T2 is equal to T2 prime multiplying the antilog of S2 minus S2 prime all over the specific heat capacity, that is Cp. So this is the formula that we use to calculate for the temperature 2, that's the temperature of the superheated vapor. So anytime you are given a question, make sure that you use this formula to get your temperature 2 because it will not be given in the question. And also, if you want to know the temperature, if you want to know the enthalpy of the superheated vapor, you see the very enthalpy of the superheated vapor can never be deducted from the refrigeration table. We have a table called refrigeration table, and for every single refrigerant, let's say from 12, from 11, from 22, almost all the refrigerants available have their own they have their own refrigeration table that we use to determine the enthalpy and then entropy at any point in time. So with the exception of the superheated vapor, with the exception of the superheated vapor, we can determine the entropy, the enthalpy, and then the entropy of the other points by using the refrigeration table. But as you can see, if you are to just consider this graph here, you can see that the 0.22 resides outside the actual curve. That is why you can't determine the enthalpy 2, that is the H2, from the refrigeration table, but you rather have to do calculation. And if you want to do so, this is the formula that we use to do the calculation. H2 is equal to H2 prime minus Cp multiplying T2 minus T2 prime. So let's put these two formulas in our mind because we'll be using them very often. We'll be using these two formulas very often. In fact, almost every question that we'll be solving, we will need these two formulas. So let's keep them at our fingertips. So I am still on the calculations. Normally, you'll be asked to calculate for what we call refrigeration load or the cooling load. The cooling load has to do with the rate at which heat is removed from a given substance in order to lower its temperature. So when a fridge has a very higher cooling load, it implies that that fridge has the ability to remove more heat, or it has the ability to remove heat faster from a given substance and then cool it down. So a fridge with higher cooling load will cool down a food or like any substance at a faster rate as compared to the one with lower cooling load. So the unit for cooling load is called ton of refrigeration, and 1 ton of refrigeration is equal to 3.5 kilowatts. You would also be asked to calculate for heat load. Heat load can be determined at the evaporator region here. That's the rate of heat exchange between the food itself, or whatever that is, whatever placed in the refrigerator, and then the refrigerants at the evaporator region. And we can determine this heat load by M multiplying H1 minus H4, where M is the mass flow rate of the refrigerant, and then H1 is the enthalpy at the point 1, and then the H4 is the enthalpy at the point 4 here. We would also be asked to calculate work done, and work done here occurs at the compressor region because it is only the compressor region that is existing as a pump, that is existing as a pump which compresses the superheated vapor into which compresses the saturated vapor into a superheated vapor state. So the work done is actually done at the compressor region. And if you want to determine it, it can be obtained by multiplying the mass flow rate of the refrigerant by the difference between point H2 and then that of H1. And if you are asked to calculate the heat rejected by the condenser, you can determine that by looking at the point where the condenser is located. You can see that we were moving from point 2 here all the way to point 3. So we can determine the heat rejected by the condenser by multiplying M and then H2 minus what? H3. Sometimes too, you'll be asked to calculate the mass flow rate of the refrigerants, and that can be determined by M. To be using the formula M is equal to Q over H1 minus the H4. And we also have what you call the coefficient of performance, and that can be determined by dividing the heat absorbed by the evaporator by the work done by the compressor. So you get H1 minus H4 all over H2 minus H1. So for the value of coefficient of performance, it ranges from 3 to 6. The value ranges from 3 to 6. Now let's look at this particular work example to check whether we have understood the concept so far. So let's consider this question. Using Freon 11 as the refrigerant, specific heat capacity of 0.8 kilojoule per kilogram Kelvin, and cooling load of 20 tons of refrigeration, determine I, the entropy of the superheated fluid H2, the COP, mass flow rate of the refrigerant, work done by the compressor. So this is the question given to us. So let's try our hands on this question. So first of all, this is the diagram, and we know that the initial temperature was at minus 10 degrees Celsius. That the temperature at the evaporator region was minus 10 degrees Celsius, and the temperature at the condenser region was also given to be 65 degrees Celsius. So the first step is to deduce the values of H1, H2, H3, S1, and then S2 from the R11 refrigeration table. As I said, every refrigerant has its own refrigeration table that we use. So when you are given a question and then you are asked to use Freon 11 and you go and use Freon 12's refrigeration table, you are automatically solving the question wrongly. You will score 0. So please pay attention to the refrigerant that you'll be asked to use for the calculation. So this is the Freon 11 refrigeration table. So from the question, we are deducing the values of H1, H3, and then H2 from the refrigeration table. So let's start with the temperature at the evaporator region, which was at the minus 10 degrees Celsius. So let's move to the table and check minus 10 degrees Celsius here. We can see that at the minus or at the evaporator region, when the refrigerant absorbed heat from the food, it existed as a saturated vapor. It existed as a saturated vapor. So from the table, we will read the enthalpy value from the saturated vapor region. Note that we have liquid region and then vapor region. We have saturated liquid region and then saturated vapor column as well. So from the columns here, we will check the value from the saturated vapor region and we will get it to be 384.64 kilojoule per kilogram. And let's find the corresponding entropy as well. Since it was existing as a saturated vapor, then we also get the entropy from the saturated vapor column as well. So from this same column, we will get our entropy of the saturated vapor at minus 10 degrees Celsius to be equal to 1.7023 kilojoule per kilogram. And we know from the refrigeration cycle that the compression of the saturated vapor from the point 1 all the way to point 2 occurred isentropically, that is at a constant entropy. So this means that the value of entropy 1, that is S1, should be equal to the value of entropy 2, which is S2. Hence, we will get S2 to also be equal to 1.0723 kilojoule per kilogram. Now, let's move on to the temperature at the condenser region. We were given the condensing temperature to be equal to 65 degrees Celsius. And we know that at that point as well, the refrigerant was existing as a saturated vapor. So, we will look at the value of the H2 prime from the saturated vapor region. Please don't mistakenly take H2 prime for H2. H2 was the superheated vapor. It was the superheated vapor, whereas the H2 prime was the saturated vapor that was entering the condenser. Don't forget that after compressing the saturated vapor that entered the compressor, you see, when it enters the compressor, it will compress it isentropically and it will then become a superheated vapor. So we have to remove some superheat from it before it will enter the condenser. So the H2 prime here, the point H2 prime here, or like the 2 prime points is the what? Point whereby the saturated vapor was entering the condenser. At that point, we no more take it as a superheat, but it is rather just a saturated vapor. So the enthalpy at that point, that is the enthalpy H2 prime, can be deduced from the from the region whereby we have the saturated vapor. That is this particular column, you can see that the enthalpy of the saturated vapor at 65 degrees Celsius was found to be 422.68 kilojoule per kilogram. And we will also get the corresponding entropy value at the same temperature to be equal to 1.6765 kilojoule per kilogram. Now for the H3, the H3 was when the H3 here represents the enthalpy of the saturated liquid. This is the only time we are mentioning liquid. Don't forget that when the condensation occurred, the refrigerant now exists as a saturated liquid, and that is when it is entering the expansion valve. So at that point, it is existing as a saturated liquid. So we will look for the enthalpy value from the saturated liquid region, and we will get the value to be equal to 257.95 kilojoule per kilogram. And I hope you have not forgotten from the pressure enthalpy chart that the value of H3 was equal to that of what? H4. And hence, we will get our H4 to also be equal to 257.95 kilojoule per kilogram. Now, let's continue with the step 2. So after getting all the parameters that I have made mention of, then let's move on to calculate the temperature of the superheated liquid before we will continue. Because if you don't have that particular T2, we can't continue with the other calculations. So we know from the formula T2 is equal to T2 prime E exponent S2 minus S2 prime over Cp. We know this particular formula, and hence we can use it to look for our T2. And we have already gotten our T2 prime. That is from what the question gave us. T2 prime was given to be minus 10 degrees Celsius. And when you convert this to Kelvin, you are going to get 363 Kelvin. Just add 273 to the minus 10, and you get this 363 Kelvin. And we also have S2 from the refrigeration table to be equal to 1.7023 kilojoule per kilogram. And then we had our S2 prime from the refrigeration table to be also equal to 1.6765 kilojoule per kilogram. And the question also gave us Cp to be equal to 0.8. So let's just fix them into the equation, and after inputting them into your calculator, you are going to get 375 Kelvin to be your T2. So the question first of all asks that's question 1. We were asked to calculate the enthalpy of the superheated vapor, that is the H2. And we have this particular formula. I made mention of this formula when I started this video, that H2 is equal to H2 prime plus Cp multiplying T2 minus T2 prime. Don't forget this formula. So just fix in the values into the formula, and then at the end you will get your H2 to be equal to 432.28 kilojoule per kilogram. And secondly, we were to calculate for the COP, that is the coefficient of performance. And I said coefficient of performance is the same as heat absorbed over work done. And heat absorbed occurred at the evaporator region, that is H1 minus H4. And this will be divided by the work done, which is H2 minus H1. And after computing everything, you are going to get 3.33. Note that COP has no units. It has no units. And the value ranges from 3 to 6. Now let's move on to calculate the mass flow rate. We were given the mass flow rate to be equal to Q over H1 minus H4. And Q here is equal to the ton of refrigeration. It is the ton of refrigeration it is the ton of refrigeration given to you multiplying the constant, which is the 3.5. And after computing the whole of this, you are going to get 0.55 kilojoule kilogram per second. So you see, the question will always give you the value of ton of refrigeration. The question will give it to you. That is the ton of refrigeration. That is the cooling load of the fridge that you are working with. So this question, we were given the cooling load to be equal to 20. And we know 1 ton of refrigeration to be equal to 3.5. So just multiply the 20 by 3.5. Sometimes you'll be given a ton of refrigeration to be equal to maybe 10. Just multiply the 10 by 3.5 and you are good to go. Sometimes too, the question will ask you to leave your mass flow rate in the form of kilojoule per minute. It will ask you to leave everything in kilogram per minute, yes. And in that case, you have to multiply the ton of refrigeration given to you. So if you were asked to leave the answer in minutes, we would just multiply the 20 by 210 and then divide it by the difference between H1 and then H4. But if the question doesn't specify anything, just go by the 3.5 kilowatts and then multiply it by the value given to you in the question. So the last Then is we were asked to calculate the work done, and we know work done to be occurring at the compressor region. So let's fix in the values into the formula, and we are going to get our work done to be equal to 26.202 kilowatts. So this is basically how calculations are done when it comes to refrigeration. I want you to try this particular question, and when you are done, comment with your answer, and I will look at it for you and tell you whether you are correct or you are wrong. Thank you very much for watching this video. Stay tuned for my other videos.